Okay, the next thing that I want to review from your algebra days is about exponents. And the reason you spend a lot of time in algebra talking about exponents is because exponents are you have to understand exponents in order to understand polynomials, okay? So I want to review exponents and then polynomials. And one of the things that we do with polynomials that usually requires some review is factoring. So we're gonna review each of those things in this section. So let's get to it. So if you have a natural number, so for some natural number n, a to the n power is just a times itself n times, right? And this works for any complex number a. A is called the base, n is called the exponent. So this is how we define exponents when on the natural numbers. But you may remember from your algebra days that we also talk about like negative exponents. We talk about fractional exponents. So we'd like to expand this definition so that we're not just dealing with natural numbers. So first of all, we can expand the definition of exponents to include all of the integers, right? And here's how we take care of that. So for a to the 0 power, we're going to call that 1 for any base a except for 0. And for a to some negative exponent, that's just going to be 1 over a to the positive exponent. Now, here's why this definition is consistent with what we've done before. Okay, so here's an argument to help convince you that this is true, right? 2 to the 4th is 16, right? Because 2 times 2 times 2 times 2 is 16. 2 times 2 is 4, times 2 is 8, times 2 is 16. Right, so 2 to the 4th is 16, 2 cubed is 8, 2 squared is 4, and 2 to the 1st is 2. So if we wanted to see like what the natural thing to guess 2 to the 0 would be, what we could do is look at all the stuff we did before and notice that to get from here to here, we divide by 2, right? And to get from here to here, we divide by 2. From here to here, we divide by 2 again. So to get from here to here, we would divide by 2. Now, if 2 divided by 2, you get 1. So it makes sense that 2 to the 0 power is 1. And you could repeat this with any other base, right? You could repeat it with 3 or with 7 or any other thing you like, and you'll notice the same thing. You're always going to end up down at 1 when you get to that base to the 0 power. The only place where this doesn't work is if the base is 0, right? Which is why in the definition I'm saying for any complex number except for 0, right? Now for that we have kind of like, that's kind of a strange case, right? 0 to the 0 power is kind of a strange thing to think about. And I have a video at the end of this lecture that you can watch if you're interested in knowing more about 0 to the 0. But continuing on with 2 to the negative 1, again, we would want to divide by 2 to get the next thing on the list. Well, 1 divided by 2 is just 1/2. And you'll notice that 1/2 is just 1 over 2 to the 1st power. If we wanted to get from there to the next place, we would divide by 2 again. 1/2 divided by 2, well, half of half is a 4th, right? So there's 1/2 divided by 2. And you'll notice that this is 1 over 2 squared. Right? So it makes sense. If you divide by 2 again, you're going to get 1/8, which is 1 over 2 cubed. And if you divide by 2 again, you're going to get 1/16, which is 1 over 2 to the 4th. So that in general, yeah, it makes sense. 2 to the negative 4 is just 1 over 2 to the positive 4. 2 to the negative n is just 1 over 2 to the positive n. Okay? Let's practice. I'll let you pause the video and see if you can work these out. Okay, I'm going to fly through my solutions now. Okay, we should get 9 here. We should get negative 9 here. We should get positive 9 there. Okay, that's kind of confusing for students sometimes. But notice that in part B, we're not squaring the negative sign, we're only squaring the 3. Right? 3 squared is 9. And then the negative sign just comes along for the ride. In part C, on the other hand, we're squaring this entire number, right? That's what the parentheses indicate. So -3 in parentheses squared means -3 times -3, and that's +9. Okay. Moving on, 27, -27, -27, and now you might feel really betrayed, right? Now you might be thinking, what? How is this not +27? Well, I mean, think about it. So in part E, you're not cubing the negative sign, you're only cubing the 3. 3 cubed is 27, and the negative sign comes along for the ride. In part F, on the other hand, you are cubing the negative sign as well as the 3. But -3 times -3 is +9, and +9 times another -3 is a -27. Okay, so be careful, right? Just be careful. 3 to the -2 should be 1 over 3 to the +2, right? So 1/9. -3 to the -2. We're not raising the negative sign to the -2 power. We're only raising the 3 to the negative power. So the negative sign is going to come along for the ride, and then 3 to the -2 is 1/9. So this is -1/9. -3 to the -2, now we are raising the negative sign to the -2 power. So this is going to be 1 over -3 to the +2. Maybe I'll write out an intermediate step on this one, right? It's 1 over -3 to the +2. That's going to be +1/9. Okay. 1/3 squared is 1/9. 1/3 to the -2 is 3 over 1 to the +2. That's 9. Okay. So you'll have an opportunity to practice a little bit more with exponents in the homework if this was really confusing to you, right? But hopefully it's not. Like I think probably most of you are probably okay with this. Okay. So moving on. In general, we don't really like negative exponents. When we see them in algebraic expressions, we like to try to eliminate them. And so the way that we do that is anytime we see a negative exponent, we change it into a positive exponent and move the base to which it's attached to the other side of the fraction bar. Now again, just be careful with the parentheses. Be careful that you're not moving things that don't need to be moved. So in part A, for example, 2x to the -1, this entire thing needs to move to the denominator, right? So this needs to be 1 over 2x. If you like, you can call it 1 over 2x to the +1, right? But that's just 1 over 2x, right? In part B, on the other hand, the 2 is not being raised to the -1 power. Only the x is being raised to the -1 power. So the 2 stays in the numerator while the x moves to the denominator, and we make the exponent positive. So 2 over x is what part B should look like. Okay, so make sure that you really have a good grasp on the difference there. Part C, well, this should look like 1 over 2x cubed. The quantity 2x cubed is 8x cubed. Right, 2x times 2x would be 4x squared. 4x squared times 2x would be 8x cubed, right? We'll talk about that in a little more detail here in a second. Whereas in part D, the -3, the exponent -3 is only being applied to the x, it's not being applied to the 2, so this should just be 2 over x to the +3. Okay. 1 over a to the -2, this, we make this exponent positive by moving it to the other side of the fraction bar, so this is going to be a to the +2 over 1, or in other words, just a squared. In part F, a squared stays in the numerator, b squared goes into the denominator. In part G, they both swap places. Okay, and then to really test if you've got the idea, see if you can do part H. Give the video a pause and see if you can do it on your own. Okay, here's my solution. Anything that has a positive exponent on it stays put. Anything that has a negative exponent on it moves to the other side of the fraction bar. So we should have e to the 4th, f to the 1st, c, oh, b squared as well, right? B squared and c, all of those things should be in the numerator. And then in the denominator, the d stays there, and the a squared joins it. That's what that one looks like. Okay, so hopefully you've got the idea. Hopefully that's crystal clear to you in case it wasn't in the past. Let's move on. So this is how exponents behave with each other. If you're multiplying two exponential expressions and they have the same base, then you can just add the exponents, right? If you're dividing two exponential expressions with the same base, then you can just subtract the exponents. If you're raising an exponential expression to a power, then you multiply the exponents, right? I'm not giving you any reasoning behind any of these rules because you should have seen the reasoning in your algebra classes in the past, and we just don't have time to rehash all of those details. But this shouldn't be new information to you, though, is what I'm trying to say. If it is new information for you, you might be in the wrong class, okay? And then we have some distribution, right? Exponents distribute across multiplication. They also distribute, ooh, typo there. Exponents also distribute across division, right? However, as I've made mention of at least 2 times already in this course, exponents do not distribute across addition, right? A plus b to the nth power is not the same thing as a to the nth power plus b to the nth power. That is simply not true. Actually, so I'm saying here, as we've seen, we haven't seen this. We haven't gone over this yet. In fact, I don't know if we ever will get to it, but this is actually what a plus b to the n power is. It's much, much more complicated than just distributing the exponent. So exponents do not distribute across addition or subtraction, but they do distribute across multiplication and division. Okay? Let's practice. When you're distributing exponents, make sure to distribute them to each factor, okay? So, in particular, something that students often fail to do is that this exponent of 3 needs to be put onto the 2 as well as the x to the 4th and the x cubed, right? So this first one would look like this. After distributing the exponent of 3, we would get 2 cubed, x to the 12th, y to the 9th, times 6 to the negative 3, x to the negative 3, y to the negative 9. Okay, now we can simplify, of course. 2 cubed is 8, so we get 8x to the 12th, y to the 9th, times 6 to the negative 3 would be 1 over 6 to the positive 3. I think that's 216. 6 cubed is 216. I'm just going to leave the variables with negative exponents on them for now, because I can use the product rule here to just add up the exponents on my like bases. So so as far as the coefficients 8 and 1 2/16 are concerned, I can write that as 8 over 216. As far as my x's are concerned, I've got an x to the positive 12 and then an x to the negative 3. I add those exponents, right? 12 plus negative 3 is 9. So I get x to the positive 9. And then y, I get y to the 9th times y to the negative 9th. I add those exponents, I get 0. So I get y to the 0. So one more step. First of all, I can simplify 8 over 216. That equals 1/27th. X, and then x to the 9th is going to end up in the numerator. So I'm going to get x to the 9th over 216. And that's it, right? Y to the 0 is just 1. So this goes to 1. This goes to, oh, not 216, 27. I'm sorry. Let me do this again. X to the 9th over 27 is what you should end up with. Right, because this reduces. Okay, So that's that. So you should be able to do things like this. It may take a little practice. Maybe you're a little bit rusty. That's okay. You'll have an opportunity to practice in the homework. Okay. Let's do another one. Part B. Oh, goodness. So we're going to have x squared negative y to the third power. That's going to be negative y times negative y. That's positive y squared. Times negative y, that's negative y cubed. So what I'm going to do is I'm just going to write the y cubed here and pull the negative sign out in front. Okay? So I've got negative x squared y cubed. And then down here I'm going to have x cubed y to the sixth. Okay? And now I can use the quotient rule, right? Whenever I have like bases, I can subtract the exponents. So I've got 2 minus 3. So this is going to be negative x to the 2 minus 3 is negative 1. Y to the 3 minus 6 is negative 2. So rewriting that without the negative exponents, I would actually write that as negative 1 over xy squared. Maybe some of you were thinking of that already, just because you were thinking, well, 2 of these cancel 2 of those and leave 1. 3 of these cancel 3 of those and leave, oh, it should have been 3, right? My apologies. Look at me making so many mistakes. But yeah, so you may have been thinking 3 of these will cancel 3 of those and leave 3 more. So if you wanted to skip this middle step, you could, of course, right? That would be fine. As long as you get there, I'm okay with it. So that's how the rules of exponents work. So now we can talk about polynomials, okay? So a polynomial is a sum of terms of the form ak x to the k, where ak is a complex number and k is a whole number. So 0 or a positive whole number, right? 0, 1, 2, 3, whatever. ak, right? ak is called the coefficient of the term. To add or subtract polynomials, we combine their like terms. And just as a reminder, like terms are 2 terms that have the same variable and the same exponent, right? They have to have matching exponents, otherwise you can't add and subtract them. When we are adding and subtracting polynomials, we like to write our answers in descending order. So we put the largest exponent first, and then the next largest exponent, and so on and so forth, until we get to the smallest term. When a polynomial is written in descending order, we call the coefficient of the first term the leading coefficient, and the exponent of the first term the degree of the polynomial. So let's practice. Let's perform the operation, and then we'll state the degree of the polynomial and the leading coefficient. Okay. So I need to go through and combine my like terms. So I have a 2x cubed here. I'm going to look through the rest of this stuff for any other x cubed terms, and I don't have any, and I don't have any exponents larger than 3. So I know that 2x cubed is going to be my first term. Then I look for any x squareds. I've got one right there. There are no like terms to combine with it, so I've got a 2x squared as my second term. Then I look for all my x to the first powers. Now I've got one there and I've got another one there. So these two are like terms. So I can combine them by adding their coefficients, right? So I've got a 3 plus negative 2. That's 1, right? So I'm going to have plus 1x. And finally, I've got a couple of constant terms. So I've got a negative 7 plus 4. That makes a negative 3. So there's the new polynomial that I get. The degree of this polynomial is 3. Right? It's the exponent of the first term. And the leading coefficient of this polynomial is 2. Right? It's the coefficient of the first term. Okay. So that's that. Here's another one. Actually, the same two polynomials, but this time we want to subtract them. So go ahead and give the video a pause and see if you can do that. Okay, here's my solution. You should get 2x cubed minus 2x squared. 3x minus negative 2x is 3x plus 2x, so that's 5x. Negative 7 minus 4 is negative 11. Okay, so there's the polynomial you get. The degree and leading coefficient are the same as they were in part A. Okay, very good. So that's how we add and subtract polynomials. And again, I know that I'm just giving you very few examples and I'm kind of running through them very quickly. It's because this should be review for you. This should just be review for you, okay? If you're rusty, that's what the homework is for, to help you kind of get back in the swing of doing algebra. All right, to multiply two polynomials, we multiply each term of one polynomial by each term of the other polynomial, so let's do it, right? If we have 12x squared times 3x minus 4, then we're going to multiply this monomial by each term of the binomial, right? So in other words, we're going to distribute it, right? 12x squared times 3x. Remember, you're going to multiply the coefficients but add the exponents. So this is going to be 12 times 3 times x to the 2 plus 1. And then, so that takes care of the first one. And then for the second one, it's going to be 12 times 4 times x to the 2 plus 0, right? Okay, part B, we've got more terms here. So we have to multiply each term of this polynomial by each term of this polynomial. We often call this foiling, right? So we're going to do 4x by both of these, and then we're also going to do the negative 1 by both of these. So they call it FOIL, you know, first, outside, inside, and last, right? FOIL. Anyway, so we get 4x squared, 28x, negative x, and negative 7. Okay, part C. We can't really call part C foiling, but it's the same idea. We want to multiply each term of this polynomial by each term of this polynomial. So starting with 2x, we're going to get 2x cubed minus 6x squared plus 14x plus 5x squared minus 15x plus 35. And then we combine like terms, right? So I've got a 2x cubed, I've got a negative 6x squared and a positive 5x squared. That gives me a negative x squared. Cross these off as I go. And I've got 14x minus 15x. That's a negative x. And then I've got a positive 35. Okay. And then one more of these. So as I've said, as I've said at least 3 times at this point, x plus 3 squared is not going to be x squared plus 9. Really, this is going to be x plus 3 times x plus 3, and then you've got to FOIL this thing, right? So you're going to get x squared plus 3x plus 3x plus 9. That's x squared plus 6x plus 9. Okay. So that's how polynomial multiplication works. So we've talked about polynomial addition, subtraction, and multiplication. We haven't talked about polynomial division yet, but we will in the future. What I want to talk about, what I want to finish off this section with is factoring. Because factoring is directly related to multiplication. Factoring is the process of undoing polynomial multiplication. Okay? So for example, a factorization of 4x squared, right? 4x squared plus 27x minus 7 is 4x minus 1 times x plus 7, right? As we've seen, as we saw in example 5b, right? So, so factoring is undoing polynomial multiplication. It's rewriting the polynomial as a product of two different polynomials of lesser degree, right? That's what factoring is. So here's a general strategy for factoring. We're going to talk about factoring a lot in this course. We're going to introduce a few new techniques, a few new factoring techniques that you may not know yet. But for now, you should remember at least these factoring techniques that I'm going to lay out here. So here's how I think about factoring a polynomial. The first thing I always do is I try to factor out a GCF if there is one. If the leading coefficient is negative, then I'll also factor out a -1. Okay, that's the very first thing I do. Now, not all polynomials are going to have a GCF, but if they do, you should take out the GCF first and foremost. Like, that's the very first thing you should check for when you're trying to factor a polynomial. Then the next thing I do is I count the number of terms in the polynomial. If the polynomial has 4 terms, then I'm going to try to factor it by grouping. Okay, and if you don't know what that means, I'll give you some examples. Okay. If there are 3 terms in the polynomial, then I'm going to try reverse foiling. In other words, if I have this trinomial here, I'm going to try to rewrite it as a set of 2 binomials, right? And to do this, I'm usually thinking to myself, I need to think of 2 numbers that multiply to be that and that add up to be that. Okay, that doesn't always work. If your leading coefficient is not 1, then it's a little more complicated than that. But still, I'm trying to think of 2 groups that when I multiply them out will give me the trinomial I'm starting with. And then finally, if there are 2 terms in my polynomial, then I can ask myself if the binomial that I'm looking at is a special binomial of some kind, right? So the special binomials are these ones, right? So is it a difference of squares? Okay, a difference of squares would look like something squared minus something squared. If it's a difference of squares, you can factor it. It's base minus base times base plus base, right? Base 1 minus base 2 times base 1 plus base 2. Is it a sum of squares? If it's a sum of squares would look like something squared plus something squared. And a sum of squares is prime. That means that it's not factorable. You can't factor a sum of squares. Okay? At least you can't factor a sum of squares over the real numbers. I'll say it that way. We'll see later on in the course that you can actually factor a sum of squares over the complex numbers, but not over the reals. Okay? Is the special binomial a difference of cubes? A difference of cubes would look like a cubed minus b cubed. Or is it a sum of cubes? And a sum of cubes would look like a cubed plus b cubed. You can factor both of those. You can factor a difference of cubes and a sum of cubes. And the factorizations are really similar looking. Now, these things you may not have seen before. Some algebra instructors don't cover difference in sums of cubes and some do, right? So you may not have seen these ones before, but anyway, notice the factorizations, right? So the factorizations work like this. Ignore the signs for now. Just look at the entries themselves, right? It's first base, second base, first base times itself, first base times second base, and second base times itself. So both a difference and a sum of cubes are going to have that pattern when you factor them. They're going to have a group of 2 and then a group of 3. In the group of 2 go the bases. In the group of 3 go combinations of the bases, right? First base times itself, first base times second base times itself. Okay. Now, as far as the signs are concerned, to fill in the signs, once you've actually filled in the entries, to fill in the signs between the entries, just look at the sign that you start with, right? So this sign is negative, and the signs follow an acronym called SOAP. Same, opposite, always positive. So this sign is the same as the sign you start with. This sign is the opposite of the sign that you start with. And this last one is always positive. It's always positive, right? So that works when you're starting with subtraction, same, opposite, always positive. But it also works when you start with addition, same, opposite, always positive. So just for the signs, just remember SOAP, same, opposite, always positive. Okay? So that's the strategy, right? You factor out the GCF if you have one, and then you count the number of terms and apply the appropriate technique based on the number of terms you have. When you're finished with step 2, you might be able to factor further, right? There might be a factor in your factorization that you can factor even further. And so you should, right? You should repeat step 2 until you cannot factor anything any further, okay? So, a lot of information there. Let me walk you through several examples. How many examples do I have here for us? 12 examples. Yeah, so I've got 12 examples of this. So let's walk through them. Let's factor 12x to the 4th plus 9x squared. The first thing I'm going to do, factor out a GCF, if there is one. So looking at these two terms, is there a GCF? The answer is yes. 3 goes into both 12 and 9, so I can take out a 3. And x squared goes into both x to the 4th and x squared, so I can take out an x squared. And now to see what I have left over, I just divide each of these terms by what I factored out, right? 12x to the 4th divided by 3x squared would be 4x squared. And 9x squared divided by 3x squared would be 3. Okay, and you can verify that you did this correctly. You just distribute this back in and make sure that you get what you started with. You should in this case, right? 12x to the 4th, 9x squared. Now, looking at this binomial, now I would ask myself, is this a special binomial of some kind? And the answer is, well, yes and no. It's sort of like a sum of squares. 3 is not a perfect square, but that's okay. I mean, it's sort of like a sum of squares, but sums of squares cannot be factored, right? Sums of squares are prime. So this is as far as this one is going to go. That's the complete factorization of that one, at least over the real numbers, okay? So there's part A. Let's look at part B. Part B. Do I have a GCF? Well, if I look at my coefficients, 2 goes into 2 and 12, but it doesn't go into 5. So I can't take out a 2. I can't take out a 5. If I look at my variables, I've got an x there, and there, but not there. So I can't take out any variables. So I don't have a GCF here, right? There's no GCF to take out in part B. So I move on to step 2. I count the number of terms, and I've got 4 terms, right? For 4 terms, the strategy is factoring by grouping. And here's how factoring by grouping works if you've never seen it before. You group the first 2 terms together, you group the last 2 terms together, and then you factor out the GCF of each group. So looking at this first group, I do have a GCF I can factor out here. I can take out a 2x squared. And if I take out a 2x squared, I'm going to be left with an x and a negative 6, right? That would give me 2x cubed minus 12x squared. From the second group, I can factor out a 5. And if I do that, then I'm left with an x minus 6, right? 5x minus 30. Notice now that you have this binomial in common. So you can factor out that binomial. If I factor out the binomial x minus 6, I'm left with 2x squared plus 5, right? So there's that factorization. That's how factoring by grouping works. Okay, let's do another one, part C. I can take out a GCF for sure, right? I can take out a 2, and I'm left with x squared plus x minus 6. Now this thing that I'm left with, it's a trinomial. So the strategy for factoring trinomials is to try to reverse FOIL. In other words, I need to try to think of two binomials that will multiply together to give me x squared plus x minus 6. And I know that they've got to have an x and an x here in order to give me an x squared there. I also know that one of these things has to be positive and the other one has to be negative, because that's the only way I'm going to get a negative 6 in this third location. And then finally, the two numbers that I put here need to multiply together to be negative 6, but then they need to add up to be a positive 1. So I think 3 and 2 will do the trick, right? This gives me x squared minus 2x plus 3x, right? That's plus 1x, and then minus 6. Now, looking at these two things left over, they can't go any further. They're not special binomials of any kind. So that's as far as that one's going to go. Okay. Here's another trinomial. This time, we don't have a GCF that we can factor out. So let's try to factor this thing. So I have a couple different options to get 8x squared. It could be like 8x and x, or it could be 4x and 2x, right? That would give me 8x squared. I'm going to guess 4x and 2x. I could be wrong. As far as the signs are concerned, again, I know that one of these things has to be positive and the other one has to be negative. Otherwise, I'm not going to get a negative 15. And then to get 15, I can try 15 and 1, or I can try 3 and 5. So I'm just going to guess and check until I come up with the right combination. So let's see, if I do 3 here and 5 there, I'm going to get negative 20 plus 6. That's not going to give me the 2 that I'm looking for in the middle. If I switch them up, I'm going to get negative 12 plus 10. Negative 12 plus 10 is negative 2. I'm looking for a positive 2. So this isn't quite right, but it's close. When you end up with the right number but the wrong sign, all you have to do is switch the signs around. Okay, so now I'm going to have a positive 12 and a negative 10. That's going to give me a positive 2. So that's my winner, I think. 4x minus 5 times 2x plus 3. Okay, you can verify, right? You get 8x squared plus 12x minus 10x is plus 2x, and then minus 15, sure enough. Okay, here's another one. No GCF to factor out. So we count up the terms, there are 2 of them. So then we ask ourselves, okay, 2 terms, is this a special binomial? And the answer is yes. This is a sum of cubes, right? This is a sum of cubes. It's like x cubed and 2 cubed right there. So the way that a sum of cubes factors is we have a group of 2, and then we have a group of 3, right? The group of 2 contains the bases, x and 2. The group of 3 contains combinations of the bases, x times itself, x times 2, and then 2 times itself. As for the signs, they follow SOAP. Same, opposite, always positive. Okay, that's the factorization. You're welcome to check this, right? If you distribute all of this stuff, you get x cubed, you get a negative 2x squared, but that cancels with the positive 2x squared there. You get a positive 4x, but that cancels with the negative 4x there. And then you get a positive 8, right? So sure enough, that factorization will do the job. Oh, you may be wondering though, can this trinomial be factored any further? You can try, right? You can try to think of 2 numbers that'll multiply to be 4 and add up to be negative 2. It's not gonna work though. These trinomials that you get once you factor a sum or difference of cubes, they can never factor further. So you're done at this point. Okay, Part F, another binomial. We can't factor out a GCF. Is it a special binomial? Yes, it's a difference of squares, right? This is x squared. This one is 5 squared, right? So a difference of squares factors as base minus base times base plus base. And that's all there is to that one. Again, you can FOIL this out and make sure that it works. Okay, wow, so many. I'll tell you what. So give the video a pause. See if you can do part G. Actually, what I'm going to do is I'm going to continue working through each of these. I'm not going to maybe give as much detail as I did on the previous page, but you should give the video a pause before each one and try to see if you can do it yourself, okay? Here I go. I'm just going to kind of blow through these. Right? Difference of squares. But the base here is x squared, right? It's x squared times x squared. That'll get you x to the fourth. This one is a sum of squares, so it can't go any further. But this one is a difference of squares, so we can factor it further. Okay. Okay, I'm going to work out part H now. Part H is kind of easy. If you like, though, you can call it x plus 2 squared instead of x plus 2 times x plus 2. I'm okay with it either way, but anyway. Part J. Okay, I'm going to factor by grouping. When I've finished, just be careful with the negative sign here, right? From this second group, I just factored out a -1, and so then you're left with a positive x and a positive 3. In the first group, I factored out an x squared, obviously, and then you're left with x plus 3. And so since these two things match, now you can factor out the x plus 3, and you're left with x squared minus 1. This is a difference of squares, though, so it goes a little bit further. I like that one. That one's a nice one. All of the terms get down to linear terms. It's pretty cool. Okay, moving on to part J. You can definitely take out a GCF. I think a 2x. And then the thing that I'm left with is a difference of squares. Moving on to part K, you can factor out a 3. And then I can try to factor that. I'm going to try 4x and x. It could be 2x and 2x. I don't really know yet. If I put the 3 here, I'm going to get a 12. I'm trying to get to 1, so I don't think that's going to work out well for me. But if I put the 3 here, and 1 there, I think I stand a chance, right? Because then I can get a 4 and a 3. So I want to do positive 4 and negative 3. That way I get a positive 1 in the middle. Moving on to part L. I can factor out a 9, I think. Yeah, I can factor out a 9. Oh, I can factor out a 27. Okay. And then what I have left is, well, it's kind of messy, but it is a difference of cubes if you squint at it just right. Oh, part L is kind of tricky. X to the 9th. So let me just say this, right? X to the 9th is x cubed, right? And 3y to the 12th. Oh, that one's even worse. But it's the cube root of 3 times y to the 4th cubed, right? So if you distribute this 3, the exponent of 3 is going to cancel off the cube root and give you a 3, leave you with 3. And then 3 times 4 is 12. So these are the two bases there. This is kind of a nasty one. I think I probably meant for not to use 81. I think I probably meant to use something that was a little bit nicer. But anyway, we can finish factoring it though, now that we know what the bases are. And this is a difference of cubes. So it's going to be base 1 and base 2. And then combinations of the bases. So base 1 times itself, base 1 times base 2, and then base 2 times itself. Oh, goodness. I mean, cube root 3 times cube root 3 is cube root 27. Nope. Cube root 9. My apologies. Cube root 9. Okay, so this should be cube root 9 y to the 8th, right? Base 2 times itself. And then the signs are going to go same, opposite, always positive. What a nasty factorization. I think I intended for this to be something else. Anyway, but that's that. Okay. So that's factoring. That's a whole bunch of factoring. One last thing that I'll say about factoring is that about this GCF business, okay? So when we factor out the GCF, we do two things. First of all, we factor out the variable part with the smallest exponent, along with the GCF of the coefficients, of course. And then to determine what's left over, we divide each term by what we've factored out. So for example, if we wanted to factor out the GCF of this trinomial, we would start off by figuring out what the GCF of the coefficients is, 36, 18, and 12. I think 6 is the largest thing that goes into each of those. So we can take out a 6. But then with the variables, we just look for the variable that has the smallest exponent, and that's the one that we can take out, right? So we can take out an x cubed. Now to see what we're left with, we divide each of these terms by this thing that we're factoring out, right? So 36x squared divided by 6x cubed, 36 divided by 6 is 6. X to the 7th divided by x cubed is x to the 4th. 18x to the 4th divided by 6x cubed. Well, 18 divided by 6 is 3. And x to the 4th divided by x cubed is x to the 1st. And then 12x cubed divided by 6x cubed. 12 divided by 6 is 2. X cubed divided by x cubed is x to the 0, which is just 1, right? And then that's that. So if we can think about factoring out the GCF in this kind of more complicated way, then we can factor kind of more complicated problems, and these things come up a lot in calculus. So let me give you an example, right? This one says factor the following expressions. We've got x times x plus 3 plus 4 times x plus 3 squared. Notice that they've both got this binomial in common. And so if we're thinking about factoring out the GCF, what we can do is take out the version of this binomial that has the smallest exponent on it. That would be this first one. So we can take out an x plus 3 to the first power. And then if we're asking ourselves, what are we left with? We divide each term by what we're taking out. So x times x plus 3 divided by x plus 3 is just going to leave us with x. And then 4 times x plus 3 squared divided by x plus 3 to the first power is going to leave us with a 4 times x plus 3 to the first power. Okay, now we can simplify that a little further. We're going to have x plus 4x plus 12. We can combine like terms. We get 5x plus 12. Okay, so you end up with something a lot more simple than what you started with. Okay, here's another example. This example has some negative exponents in it. Remember, we can always factor out the variable that has the smallest exponent on it. So let's see what we get in this case. So first of all, with the coefficients, it looks like we can take out a 3. And with the variable, we can take out this variable with the smallest exponent. That would be x to the negative 3. So we can actually factor out an x to the negative 3. Okay? Now to see what we're left with, we take turns dividing each of these factors, or sorry, each of these terms by this GCF that we factored out. So 9x squared, let's think about this. 9x squared divided by 3x to the negative 3. The 9 and 3 are going to cancel and give us 3. And then the x, we're going to do 2 minus negative 3. That's 2 plus 3. So that's x to the 5th, right? So we get 3x to the 5th after we factor out the 3x to the negative 3 from that term. We can do the same thing with 6x to the negative 1, right? 6x to the negative 1 divided by 3x to the negative 3. 6 divided by 3 is 2. X to the negative 1 divided by x to the negative 3. We're going to do negative 1 minus negative 3. That's negative 1 plus 3, which is a positive 2. Right? So we're going to get a 2x squared. And then finally, 12x to the negative 3 divided by 3x to the negative 3. 12 divided by 3 is 4. X to the negative 3 divided by x to the negative 3 is 1. So we get a minus 4. Okay, and that's how we would factor out the GCF of that one. Okay, so let me give you one more example. This one kind of combines both of the previous ones because in the sense that we've got binomials in common, but we also have some negative exponents going on. So let's see what we can factor out here. First of all, I can factor out, if I'm looking at the coefficients, I can factor out a 4. And then if I'm looking at the variables, this one has an x on it, but this one doesn't. However, they both have an x plus 7 in common. So I can take out an x plus 7 raised to the smallest exponent. That would be negative 1 in this case. Now to see what we have left over, we're going to take 4x times x plus 7, and we're going to divide it by 4 times x plus 7 to the negative 1. What do we get? Well, the 4's cancel. I'm left with an x to the first power, and then I'm left with x plus 7 to the first divided by x plus 7 to the negative 1. So that's going to be x plus 7 to the 1 minus negative 1. That's 1 plus 1. So that's x plus 7 to the positive 2, right? That's x plus 7 squared. So I've got x times x plus 7 squared left over there. For the next term, I'm going to do 8 times x plus 7 to the negative 1 divided by 4 times x plus 7 to the negative 1. That's going to give me 2, right? So that one is just 2. Okay, I think we can simplify that a little bit. We've got 4 times x plus 7 to the negative 1 times x times, if I FOIL this out, I'm going to get x squared plus 7x is 14x plus 49 plus 2. I'm going to have 4 times x plus 7 to the negative 1 times x cubed plus 14x squared plus 49x plus 2. Okay, and that's that one. So these kinds of things can be a little bit complicated as well, but again, if you just follow these two suggestions, first of all, factor out the variable part with the smallest exponent, and second of all, determine what's left over by dividing each term by what you factored out, just like we did here, then you can't go wrong, right? You can't go wrong. You'll end up at the right place. Okay, so that will do it for 2.2. Another long section, kind of.